Have you ever stopped to think about what everything around you is made of? From the air you breathe to the desk you're sitting at, it's all matter. In science, we define matter very simply. Anything that has mass, it weighs something, and takes up space. It's the foundational concept for all of chemistry and physics. And to really understand it, we have to look much, much closer than the naked eye can see. So if everything is matter, what is matter made of? Imagine breaking something down into the smallest possible piece that still is that thing. That's essentially what an atom is. Atoms are the absolute basic fundamental units of all matter. They are so tiny, it would take millions of them lined up to equal the thickness of a single strand of your hair. They are the tiny, invisible bricks that build your entire world. Now let's zoom into the atom itself. It's not just one solid ball. It has a structure, kind of like a miniature solar system. Right in the center is the nucleus, which is extremely dense. It holds almost all the atom's mass. Think of the nucleus like the sun in our solar system. It's the heavy, central component. What two important subatomic particles do you think are locked inside this dense core? One of the most important residents of the nucleus is the proton. Protons have a positive electrical charge. The number of protons an atom has is its superpower. It is the one thing that decides what element the atom is. Change the number of protons, and you change the element entirely. It's like a scientific ID card. If an atom has 8 protons, it must be oxygen. If it has 6, it must be carbon. The other main resident of the nucleus is the neutron. Neutrons are the great neutralizers. They have no electrical charge at all. They mostly act like a kind of glue or buffer, helping to keep the positively charged protons from repelling each other and flying apart. They contribute significantly to the atom's mass, but they don't change its identity like the protons do. Orbiting outside the nucleus are the third key subatomic particles, the electrons. Unlike the protons, electrons carry a negative electrical charge, and they are incredibly small and light, thousands of times smaller than a proton or neutron. Electrons zip around the nucleus in specific paths called shells or energy levels. These are the particles that are constantly in motion and determine how one atom will interact with another, essentially creating all the chemical reactions we see. For an atom to be balanced and stable, we call this a neutral atom. It needs to have the same amount of positive charge as negative charge. That means the number of protons, plus, must exactly equal the number of electrons, negative. If you have a group of 10 friends and 10 enemies, the net impact is 0. It's the same with atoms, a perfect electrical balance. If this balance is thrown off, the atom becomes an ion, which is a charged particle. But that's a topic for another lesson. When all the atoms in a substance are exactly the same, they all have the same number of protons, you have what scientists call an element. Think of elements as the primary colors of matter. You can't break them down into simpler substances. Whether you have a giant gold bar or a tiny atom of gold, it's still the element gold. It's the simplest, purest building block we have. Every single element has a special number called the atomic number. We already talked about what makes an element, its unique count of protons. So, the atomic number is simply a count of the protons in the nucleus. This number is the main way the periodic table is organized, making it the most important piece of information you can find about an element. It's the element's DNA. While the atomic number tells us who the atom is, the atomic mass tells us how heavy it is. Since protons and neutrons are much heavier than electrons, we calculate the mass by simply adding up the number of protons plus the number of neutrons in the nucleus. It's the total count of the heavy particles. Knowing both the atomic number and the atomic mass lets us figure out all the basic structure of a neutral atom. With over 100 elements now discovered, scientists needed a powerful way to organize all this data. Imagine a library without any organization. You'd never find a book. The solution is one of the most brilliant organizational tools in science, the periodic table of elements. It organizes all the known elements in a way that lets us predict their properties just by looking at where they are placed. The genius behind the original organizational chart was a Russian chemist named Dmitry Mendeleev. In 1869, he created a version of the table. What was so incredible is that he left gaps. He was so confident in his pattern that he predicted the existence and properties of elements that hadn't even been discovered yet. Imagine telling scientists exactly what a new element would be like before they had found it. That's scientific brilliance. The reason the table is so predictive is due to the periodic law. It's a fancy way of saying that the properties of the elements, like how they react or look, don't change randomly. As you move across the table, these properties follow a repeating pattern. It's like a repeating chorus in a song. You can almost guess what's coming next because of the pattern. Let's learn how to read the map. The horizontal rows on the table are called periods. There are 7 periods. Elements in the same period don't share similar properties like elements in a column do. Instead, they tell you about the electron shells. All elements in period 2, for example, have 2 electron shells around their nucleus. It's a count of the energy levels. The vertical columns are called groups or sometimes families. There are 18 groups. These are the truly powerful organizing feature. Elements that are in the same group share very similar chemical properties. Why? Because they all have the same number of valence electrons, the electrons in the outermost shell, which are the electrons that determine how an atom will react with others. Let's look at an example group. Group 1 elements, known as the alkali metals. These are some of the most reactive elements on the entire table. Think of sodium, Na, or potassium, K. They want to get rid of that single outer electron so badly that they react violently with water or air. If you saw a demonstration, you'd know why they're stored in oil. Now look at the other extreme. Group 18, the noble gases. These are the cool kids of the table. They are completely non-reactive or inert. Why? Because their outermost electron shell is completely full, making them perfectly stable and happy. Neon and argon are examples. They don't want to gain or lose any electrons, so they make great safe gases for things like light-up signs. To make reading the periodic table even easier, all the elements are organized into 3 big categories. The vast majority, on the left and center, are the metals. On the far right are the nonmetals. Separating them is a staircase or zigzag line of elements called the metalloids. This 3-way split helps you quickly understand the most basic properties of any element. Most of the elements you're familiar with are metals. Think of aluminum, iron, or copper. They all share common properties. They are great at letting heat and electricity pass through them, good conductors. They are shiny, and they can be bent or hammered into shapes, malleable, or stretched into thin wires, ductile. These properties make them perfect for building, cooking, and wiring homes. On the other side, nonmetals are the opposite. They're usually poor conductors of heat and electricity, insulators, and they're often gases like oxygen or brittle solids like sulfur. The elements along the dividing line are the metalloids. They're like chameleons, showing properties of both metals and nonmetals. The most famous metalloid is silicon, which can conduct electricity just enough to make all the computer chips that run our phones and laptops. That versatility makes them incredibly valuable.